last topic for today. And the last topic for today is going to actually help us understand what happens when we connect lambda components to transmission lines. I'm going to give you two specific cases that occur very often in real life. First, we're going to look at the shunt case, which essentially means that we have a transmission line and we connect a load in parallel to this transmission line. So I have a load ZL connected in parallel to this transmission line, and I really want to understand how to analyze that situation. It happens again very often. We connect many components, many modules, many different devices in shunt in transmission lines. So the key to analyze this circuit is to just look at the physics of the circuit by first imagining what happens if you launch an incident plane wave. Essentially, if you launch an incident plane wave, normally that plane wave would simply continue propagating through the line, except that when it hits that load, as we discussed before, we will necessarily have a reflected wave, and then we will have a transmitted wave. So I have written down here some equations that you can use to express these waves. So as usual, the incident wave will be V0 plus times e to the negative j beta z. We're now again in the lossless regime, where this V0 plus is assumed to be known, and it is the wave that has been launched from the left-hand side. The reflected wave is propagating towards the negative z-axis, so it's going to have a magnitude which we assume to be gamma, some type of reflection coefficient, times the incident magnitude, V0 plus, and we will have the e to the j beta z, which is the phase constant as the wave is propagating to the negative z. Gamma, of course, is unknown, and we will be trying to find out this as we will see in a minute. Of course, the total wave on the negative z space is going to be both the incident and the reflected wave. Now, on the right-hand side, after the load, we will only have the transmitted wave, which will have now another magnitude, some coefficient tau, which is the transmission coefficient, which is also unknown, the known magnitude V0 plus, and then e to the negative j beta z, since this is propagating to the right-hand side. So now the key is we need to find basically gamma, and we need to find tau. So how do we find those? We find those by essentially ensuring that I have a continuity equation at the boundary condition, at my boundary. So my boundary is right here that separates the left-hand side with the right-hand side. Conventionally, we will assume that this is equal to 0. Of course, if it's somewhere else, you can apply it somewhere else. But when it's equal to 0, at z equals 0, my voltage on the left-hand side should equal my voltage on the right-hand side. This is required from a voltage continuity point of view. And so when I enforce this continuity boundary condition at z equal to 0, I can express the waves as I just showed you before. And then once I do that, I will get that V0 plus gamma V0 plus, incident and reflected wave at z equal to 0, must be equal to the transmitted wave at z equal to 0, which is tau times V0 plus. So that is a single equation that will allow me to calculate now the reflection coefficient, as you will see here. So the reflection coefficient essentially will be equal to gamma in minus z naught over, z in minus z naught over z in plus z naught. And so if I try to calculate this reflection coefficient and I look at what my z input impedance is, it actually doesn't take much to see that the input impedance z is simply ZL in parallel with z naught. So let me write it here. This will be ZL in parallel to z naught. And why that's the case, ZL is the impedance of the load, and Z naught is the impedance that you will see in this semi-infinite transmission line. So Z in is equal to ZL in parallel with Z naught, so I plug it in here, as you will clearly see from this equation, and now the reflection coefficient gamma is going to be equal to negative Z naught over 2ZL plus Z naught. And finally, I can find my transmission coefficient from this equation right here, as tau to be 1 plus gamma. And if you do the math, it will be 2ZL over 2ZL plus Z naught. So let me show you very briefly what happened. Again, I'm enforcing the continuity equation, and I'm finding an equation that actually relates gamma with tau. So now I can find my gamma just by looking at my circuit, and I can find tau as 1 plus gamma. That is the case of the shunt load, and as I mentioned, that is of great practical importance, so I would strongly recommend that you know how to do this calculation. The last case of practical importance is when I have a series case. And this is slightly more complicated. It's also not as easy for us to see because we have to draw a series load that connects the left-hand side of the line with the right-hand side. But yet, because the load is lumped, both this point as well as this point correspond to z equals 0. And I know that when we're thinking about it from a geometry point of view, that doesn't actually seem reasonable. But when you look at it from an electrical point of view, a lumped load means it has a physically 0 size. And so that means that both of these nodes sit at z equals 0. Now, besides this complexity, everything else, the analysis technique, is actually identical. We have some type of an incident wave, same equation as I had before, some type of a reflected wave, same equation as before, some type of a transmitted wave, exactly same equation as before. The key now is to find the continuity equation and to find the reflection coefficient. The reflection coefficient is what I'm going to start with because it's by far the easiest. In fact, it's shown right here. So reflection coefficient at the location of the load will be equal to z in minus z naught over z in plus z naught, as we already know. And then if I look at now what is z in, it's just the zl in series with this z naught. So simply z in here is replaced with zl plus z naught. And here I've made the assumption that the left-hand side characteristic impedance is the same as the right-hand side characteristic impedance. So the result is very simple. The gamma will be equal to zl divided by zl plus 2z naught. Most people can do that quite well, and there is really no complexity there. However, where a little bit of complexity comes is that a common mistake is that sometimes people will assume that tau, the transmission coefficient for this wave here, is the same as it was before for the shunt case, and tau, they will say, is equal to 1 plus gamma. As we will see, that's a mistake, and that's not true. I think the reason for that relatively common error is because the shunt case is discussed far more often in textbooks than the series case. And so naturally, if that's the only thing you have seen, you will always assume that no matter what, tau is equal to 1 plus gamma. And unfortunately, for the series case, that is simply not true. So let's see how we can truly find the correct tau. We can truly find the correct tau by, again, applying the continuity equation. The continuity equation, as a reminder, is the equation you have to enforce for the voltage at the location of the load. So I have to make sure that the voltage at the location of the load at z equal, for example, z naught plus is equal to the z is equal to z naught minus. But because now my load is in series, I have a voltage division happening right here. So if I look at, for example, how much voltage I have here, this is the V transmitted at z equal 0 plus. It's going to be basically the voltage that I had here, which is this part. But I have a voltage division that happens between the input terminals and this load. So the transmitted voltage is not just V incident plus V reflected at z equals 0 minus, but is V incident plus V reflected with this voltage division formula. And really, that's the only complexity, which is very simple if you look at the circuit carefully. But again, most people have never experienced this before, so they will naturally apply what they already know. So if you look at this equation now, essentially you can get this equation that clearly links tau with gamma. And as you can see, once you get the V naught plus out of the way, tau is not 1 plus gamma. It's actually 1 plus gamma z naught over zl plus z naught. So that's really the right equation for tau, the transmission coefficient. And once you know that, you're basically done, because we just calculated what gamma is right here. and now we calculate what the transmission coefficient is right here.